Hello everyone. In this lecture, we're going to study the detailed contents provided in lecture note number 9. So we're gonna begin the uh, how to understand all the details introduced in section 3.3, which is the last chapter of last subsection of chapter 3. Okay, let me see. I guess we should. So, I guess I need to go back to this. Okay, looks better. Okay, so in this lecture 9, we're gonna start with figuring out the definition of generation and recombination. So in device physics, whenever we are talking about the word generation, this indicates a process. This is a certain process by this process, what uh, electrons and holes, those two representative carriers in crystalline silicon material. So those two carriers, electrons and holes, are created in pairs. Okay, so this process, because of this generation process, electrons and holes are created in pairs. Then this process is named as generation. Okay, so in device physics again, whenever we are talking about generation, which means two major types of carriers, such as electrons and holes in silicon crystalline materials, are created, generated, right? Made in pairs. EHP, right? EHP, electron hole, created in pairs. So this whole process is named as generation process. Okay. And the next concept is recombination, which is quite opposite concept of generation. Okay, so that's the reason why recombination is always explained with the help of generation. So recombination is followed by generation. So why is that? How come the recombination is introduced right after the generation? Because simply speaking, the generation is always happened right after the generation. Is that the truth? Is it true always? Not really. Go back to the concept of dynamic situation. Again, dynamic situation. So we have learned that at room temperature, the total number of free electrons available in silicon crystalline material is 10 to the 10 per cubic centimeter. Then we have learned that those 10 to the 10 electrons are available in terms of the total number of electrons, but in terms of which specific electrons, those 10 to the 10 electrons is dynamically varied. I mean, the very first electron out of 10 to the 10 electrons is not anymore available maybe a few seconds later. Why is that? Within a silicon crystalline material, those electrons would be recombined with the other holes, and a totally new electron should be created simultaneously, so that the total number of electrons, that is 10 to the 10 per cubic centimeter, is still kept well. So this is named as a dynamic situation. Okay, so that is the main physical origin why we should learn recombination and generation together. Okay, so now you can write down the definition for this recombination. What is it? Recombination is another process by which what would be happened by this recombination process? Yes, electrons and holes, those two carriers are recombined. In other words, annihilated, or simply speaking, killed. Okay, or removed in pairs. Okay, so electrons and holes are annihilated in pairs by what process? Yeah, recombination process. So generation and recombination processes work to change the carrier concentrations. That's true. And because of these generation recombination processes, the total amount of current flow in device, such as MOSFET, MOS capacitor, PN junction diode, MS diode, would be indirectly affected. So whenever we are talking about how much current can be flown in your own device, well, we should understood how much drift and diffusion currents are formed. In addition to that, generation recombination would become another player in contributing to the total amount of current flow in your device. Okay, all right. So now let's move on to some more details on the generation processes. So on the left hand side, you can see the band to band generation process, which is say number one. And the second type of generation process is recombination generation center. Okay, so with the help of these RG centers, the generation can be happened. And the last type of generation process is the impact ionization. So first of all, we should understand what the impact ionization is first to better understand the concept of generation process by impact ionization. So okay, let's move on to the first one, band-to-band generation. This is a very typical one and general one, and you have already understood this concept whenever we are talking about how the electrons and holes are created in pairs, right? So, this original electron is captured within, the covalent bond between two neighboring silicon atoms. And because of thermal energy coming from outside, the electron is excited and it has a more, much higher energy so that it can stay at a energy level which is way higher than the original energy state that that electron has previously set. So because of the thermal energy, the electrons can be excited into a higher energy state so that free electrons and free hole, those are two carriers are created in pairs. Okay, so usually thermal energy, but in some cases, the light, photon, not phonon. Okay, phonon is vibrating silicon atoms, and photon is light. So light or externally applied thermal energy are given, then electron pairs are created. And in this specific case, electrons and holes are created by band-to-band generation process. Okay, let's move on to the second one. Second one is quite interesting. Instead of electron is moving from valence band to the conduction band directly, in this specific case, electrons can jump into another energy state and then jump into the conduction band. So two more steps are necessary. So previously, in the case of band generation, electron has jumped into the conduction band at a time, one time. But in this case, it needs two different steps to get into the conduction band. So then previously we have learned that in the band gap energy, in the band gap, there is no energy state available. That's the main reason why the electrons cannot exist. As I asked you in homework problem sets, electrons cannot be existed in the band gap energy, right? Because of no energy state available for these electrons to keep staying. However, well, this stuff is valid when the silicon crystal material is perfectly created, fabricated. But because of the its own intrinsic and unique defects uh, in silicon material, so that defect's energy state is quite well matched to the certain energy level in between conduction band edge level and valence band edge level. Well, definitely a certain defect could create the energy state in conduction band or valence band. That's true. But what if the defect can create the energy level in between EC and EV, then this energy state would work as what? As recombination generation center. So this RG center plays a key role to create the electron hole pairs. So what is the main difference between type number 1 and type number 2? In order to create electron hole pairs, in the type number 1 band-to-band generation, what is the minimum required energy to have one single set of electron and hole? Yes, band gap energy, right? EC minus EV. This band gap energy is the minimum required energy to create electron hole pairs. What about the type number 2? How much energy, minimum energy is necessary to create electron hole pairs? Suppose that this RG center energy state is in the mid gap. So this energy value is Eg over 2. Then how much energy is minimally required? Still, can you answer band gap energy? Because in the end, this electron should move up and up. So we need Eg over 2 plus another Eg over 2. No, you're wrong. The minimum required energy to have, to induce one single set of free electrons and holes is Eg over 2, because the externally supplied thermal energy is constant, kind of constant. So once Eg over 2 energy is supplied to a certain electron into the certain electron of covalent bonds, then this electron would excited up to this RG center energy state. And still this Eg over 2 energy can be supplied into this electron, then it will go into and capture any energy state in the conduction band. So Eg over 2 is a minimum required energy. So again here, with the help of this energy state placed at the mid gap, would be the kind of RG center. Center means when you have a chance to travel abroad, once you have no idea and you're lost, then you're gonna drop by the information center. So why the place is named as information center? Because at the center you're gonna get a bunch of information uh, on the site that you're traveling. So same here in the silicon crystal material. So that center, what is the main role of the center? Well, it is making and creating and invoking the recombination generation. So that is named as RG center. Okay, all right. Then one more tricky question is, what if the energy state of a certain RG center is matched to this energy level? Then what is a minimum required energy to create single set of electron hole pairs? This or that or whole band gap? One, two, three. Which one is the minimum required energy to create one single electron hole pair? Yeah, the answer is number 2, but still smaller than the band gap energy. So in any case, whatever the energy state is, as long as a single energy state is created and obtained by this any defect, then the minimum required energy to create electron hole pairs compared against this case, always is smaller, right? Okay, now let's move on to the last case, impact ionization. So I guess we need to first figure out what the impact ionization is. As shown in this energy band diagram, take a look at that. There is a band bending. ECEVs are sloped, right? So previously I said DEC over dx 1 over q time is equal to electric field. So since dEc over dx is non-zero, right? So this electric field is non-zero. In other words, the voltage difference here plus volt, here minus volt, and electric field is formed, right? So under a non-zero electric field, this impact ionization can be happen. But the question is how strong the electric field intensity is. Depending, well, the electric field intensity can be converted into the how sloppy of this conduction band edge is, right? So because first the derivative of a conduction band edge with respect to x is proportional to the electric field. So your electric field intensity can be illustrated by simply drawing the slope of the conduction band edge. Okay, now because of this electric field, a single electron, free electron in conduction band can be accelerated because of this, force. Force is minus q times electric field, as we have learned in the, drift section, right? Chapter 3.1. So electron is accelerated and its velocity is non-zero, and it is its velocity is increasing a lot. And at some point, this electron would lose its own kinetic energy. How to define the kinetic energy of electron in conduction band? Yeah, the energy state of electron and the conduction band edge, right? So this energy difference is defined as a conduction band kinetic energy. Suppose that this at this spot means that say x of L, at this position, electron has now hit the silicon atom or phonon, right, vibrating silicon atoms, and is going to lose its velocity. In other words, it stopped, right? So once it is stopped, its velocity is zero, so kinetic energy is also zero. So there is no energy difference. So electron is now sitting at this energy state. But still, this electric field is available, so it is going to accelerate it again, and it is going to hit the silicon atoms phonon, and it's going to lose its kinetic energy. And again, it is going to be accelerated. So this whole repeated process will be kept as long as this electric field is available. Okay, but here in this case, what I want to say is, what if this kinetic energy that this electron has lost is 1.5 times Bank gap energy? So 50% more Bank gap energy, 1.5 times Bank gap energy. So 1.5 times 1.12 electron volt. If this kinetic energy is slight equal or greater, higher than 1.5 times 1.12 electron volt, and this lost energy would contribute to induce another one more free electrons coming from the covalent bonds between two neighboring silicon atoms, and a single hole would definitely create it. So now two electron and one hole are left, right? Originally there is a one single electron, but now if as long as this kinetic energy is higher than 1.5 times band gap energy, then these electron hole pairs are created. Okay, I guess here 0.5, so 50% of band gap energy has been used to consume uh, to ignite. Do you know this word ignite? 발화시키다 in Korean. Yeah, to ignite the first uh, electron hole pairs, to ignite ignition of making the very first electron hole pair sets. Okay. Anyhow, once this kinetic energy is high enough, how high enough? We can quantify 1.5 times band gap energy. Then two electrons are available. Then those two electrons would be accelerated together, and it's going to lose another kinetic energy. Then two more electrons would be induced. So now total four electrons are available, and they are going to accelerate it again, and maybe at the end of this place, exponentially increased uh, number of electrons are available at the end of this sample. Okay, so this impact ionization would induce another new set of electron hole pairs. This is another type of generation process. Okay, so please understand the physics how electron hole pairs are created by three different processes: band to band, Origin center, impact ionization. Okay, now let's move on to the details on the recombination process. In this slide, it's all the processes introduced shown in this slide is quite opposite process of the process that we have learned in previous slide. So here, the very first type of recombination process is a direct recombination process. So direct means electron available in conduction band has met with a hole in valence band, and those are two electrons, those two carriers, electrons and holes are annihilated, killed, and recombined together. Then maybe as a result of this recombination, the energy would be supplied to outside. But what kind of energy that can we get from this direct recombination process? Well, it depends. In some cases, it would be light. In some cases, it would be thermal energy. Okay, so maybe in Intel CPU, if this direct recombination has been happened, maybe that recombination process would give us a too much amount of heat, thermal energy. Well, what if this recombination is happened in LED light emitting diode on the ceiling of your room? Then it would give us the light, which is good, right? So, depending on the material that in which this direct recombination process is happened, or depending on what kind of engineering solution techniques has been used, that we can take advantage of using this direct recombination process to create a useful way of useful research that we would prefer. Okay, all right. The second one is RG Center, same name, but this RG Center works as the key role, contributes. This RG center can contribute to induce a recombination process. So let's take a look at some details how electrons and holes are met together. Here, in electrons in conduction band has lost a certain amount of it. In this case, I guess it looks like a energy state induced by defect is half Wenger energy. Okay, so this have at this energy level, the energy the newly created energy state is placed at the mid gap. And again here, T means a trap. So this free electron would be trapped or get into this trap, this specified site. And this hole is also trapped and captured into this trap. So at this energy state, electron holes are met together so that they are annihilated in pairs so that recombination process has been happened with the help of this trap energy state or recombination generation center. Okay, but this is one specific example how the recombination is happened via RG center. But on the right hand side, you can see that this electron in conduction band has lost its energy by band gap over 2, and another uh, process of losing its energy by band gap of 2. Then in the end, this electron would match with the hole at imbalance band, and those are two carriers are annihilated in pairs. So um, these two types of specified RG center process would be considered as a recombination process. Okay, all right. The last type of recombination process is illustrated on the right hand side. So here, can you pronounce it? Can you speak? Can you say this word by yourself? A few students would say, would speak ogre stuff or something, or oze or something. But the exact pronunciation of this word is OJ, okay? OJ, again, OJ. So OJ recombination is the last one for recombination process. So this what let's take a look at how the OJ process has been done. So suppose that there is a single electron in conduction band and it's going to lose its energy by direct recombination process. Then, as we have learned, this the lost energy would be delivered and converted into a different type of energy. But in if OJ recombination is happened, this the energy that this electron has lost would be delivered to the other electron in conduction band, and this electron has observed this amount of energy, in this case a band gap energy, then it's going to be excited and sitting at a energy level which is way higher than the way away from the conduction band edges. And afterwards, this electron is going to, dynamically moving and roam around in conduction band, and in the end, it's going to lose its own energy, and it's going back to its original energy state. And in this process, many thermal energy would be delivered to outside. Okay, so this uh, process, this it looks like a slightly complicated, but this whole process is named as OZ recombination process, and how the electrons in conduction band can create a too much amount of thermal energy by OZ recombination process. Okay. On the bottom line, you can see that a very key sentence that I want to deliver to you. Recombination in silicon material. Silicon material is a mainstream and major material for DRAM, NAND, and CPU, GPU. All the integrated circuit chip are created and fabricated onto the silicon substrate wafer, right? So in silicon material, recombination is primarily happened throughout recombination generation standards. In other words, the perfectly crystal in terms of crystallinity, perfect silicon material is not available on our hands. Okay, so that is the main reason why recombination in silicon is primarily via RG centers. Okay, all right. So we have learned some brief introduction on generation processes as well as recombination processes over the two last previous slides. And now let's slightly switch the gear and let's take a look at direct versus indirect band gap materials. In other words, previously we have learned the EX diagram, right? We have drawn the energy band diagram, which means the energy of electron versus physical distance in silicon material. But in this slide, what about drawing the energy versus K diagram? So what is this K? K means the momentum of free electron. Okay, so on the y-axis, let's place the energy of free electron, and on the x-axis, let's place the momentum of free electrons. Then what kind of curve shape can we obtain, and can we expect, can we predict? Based on your knowledge, we can do that. Energy of free electrons in conduction band is most likely kinetic energy, right? So Mn asterisk times thermal velocity. And let's simply think this is simply M, and that is velocity V. And we can convert, okay, rewrite the equation again, and 2m mv to our square, and that is 1 over 2m, and mv means mass times velocity indicates the momentum, right? in Korean, 운동량, right? So denoted as K, okay? So K square. Then energy is proportional to the K square, and the coefficient is 1 over 2 times effective mass of electron. So the curve shape, what if we draw the energy versus K diagram? Here energy is 1 over 2m times K squared. So it looks like this, okay? So now you can see that here a big curvature can be formed, okay? So this parabola shaped curve can be obtained in EK diagram, okay? All right, so now this parabolic curve uh, has been created for free electrons in conduction band, and another upside down parabolic curve is for holes, okay, in valence band. Okay, and this minima and maxima point, those two energy difference is defined as a band gap energy. Okay, and what if this, suppose that there is an electron available, right? Because this is the minimum energy level, so all the electrons would prefer to sit down on this energy state. In other words, the probability of finding electrons in conduction band would be the highest near the conduction band edge. As you have solved in homework problem sets, the uh, the energy state where the most number of electrons can be found is not exactly at the conduction band edges, but exactly at the slight energy state, which is slightly higher than the conduction band edges, which is, EC plus KT over 2. Okay. Some more detailed solution will be provided sooner or later in iCampus. I'm going to post it. Okay. And okay. So now I have drawn the electrons energy versus momentum, and this the EK diagram on the left hand side is one type of the silicon materials, just the semiconductor materials. On the right hand side, you can see another type of EK diagram for semiconductor materials. What is the main difference between two figures? Think about this. Yes, the minima maxima are well aligned, but in this case, minima and maxima has misaligned. What is the physical meaning of this? Yeah, very simple. When the electron has losing its energy, there is no change in its momentum. Without any change of momentum, the electron can lose its energy. But on the right hand side, the electron is going to lose its energy, but its momentum has also been varied, modified. Okay? So more, if I'm saying it generally, uh, suppose that we have a single electron, and now let's imagine that this electron is going to lose its energy. What if this electron is changing its momentum while the process of losing its energy? Then we can say that this electron is sitting and living in semiconductor material, which is indirect material. Okay, but if that electron in conduction band has lost its energy without any modification of momentum, no change in momentum, but there is a change in energy, then we can say that this electron is living and available, existing in semiconductor material, which is direct bandgap material. Okay, so direct material versus indirect material. What is the main criteria to classify two different type of material, semiconductor material? Yes, momentum change. If there is any change in momentum, then we can say that this semiconductor material is indirect band gap material. If not, it is direct band gap material. But to better memorize these two words, silicon is the most representative material of indirect band gap material. In other words, it would generate lots of energy because of momentum change. But in this case, gallium arsenide, such as 35, compound semiconductor material, right? So any more conventional material used in optoelectronics, any semiconducting material who can create light, not 100%, but almost 100% probability that semiconductor material is direct materials because little change happened in momentum when the electron is losing its energy from conduction band down to valence band. Okay. All right. So in this slide, please remember how to draw the EK diagram. So why parabolic curve has been obtained in this EK diagram, and take a significant look at how the momentum is changed depending on what kind of material system that we are in. Okay. Okay, so that's all for the direct versus indirect band gap materials. So if you're interested in more details on this stuff, I guess it is slightly beyond the scope of this lecture. If you're interested in more details, direct, indirect, and EK diagram, please go to the solid state physics textbooks, such as I'm going to strongly recommend Introduction to Solid State Physics, written by Kittel, who is the professor in UC Berkeley. So I guess yeah, Kittel's book is really noble textbook in the field of solid state physics. So I guess we do not have too much time to go over all the details, but if you're really interested in how the EK diagram is formed and how much EK diagram is important in understanding how much light can be emitted out of the direct band gap material, then those kind of stuff, then please go back to the introduction to solid state physics authored by Professor Kittel. Okay, so now let's take a look at another concept of access carrier concentration. I guess this slide is the very first beginning, the very first slide for MS junction and PN diode junction, PN junction. So access carrier concentration, this concept is the very first step. So I guess we need to take a short break time. So I'm going to stop my lecture here, and I would like to record another movie clip to introduce the concept of access carrier concentration, the very first step to understand PN junction and MS junction. Okay, that's all for today's lecture, and see you in the next movie clip. Thank you.